A classical computer performs operations using classical bits, which can be either 0 or 1. Now, in contrast, a quantum computer uses quantum bits, or qubits, and they can be both 0 and 1 at the same time. And it is this that gives a quantum computer its superior computing power. There are a number of physical objects that can be used as a qubit: a single photon, a nucleus, or an electron. I met up with researchers who are using the outermost electron in phosphorus as a qubit. But how does that work? Well, all electrons have magnetic fields, so they're basically like tiny bar magnets. And this property is called spin. If you place them in a magnetic field, they will align with that field, just like a compass needle lines up with the magnetic field of the Earth. Now, this is the lowest energy state, so you could call it the zero state, or we call it, for the electron, spin down. Now, you can put it in a 1 state or spin up, but that takes some energy.
If you took out the glass from your compass, you could turn the needle the other way, but you would have to apply some force to it. You have to push it to flip to the other side. And that is the highest energy state. In principle, if you were so delicate to really put it exactly against the magnetic field, it would stay there.
Now, so far, this is basically just like a classical bit. It's got 2 states, spin up and spin down, which are like the classical 1 and 0. But the funny thing about quantum objects is that they can be in both states at once. Now, when you measure the spin, it will be either up or down. But before you measure it, the electron can exist in what's called a quantum superposition, where these coefficients indicate the relative probability of finding the electron in one state or the other. Now, it's hard to imagine how this enables the incredible computing power of quantum computers without considering 2 interacting quantum bits. Hello. Hi. Now, there are 4 possible states of these 2 electrons.
You could think that, well, that's just like 2 bits of a classical computer, right? If you have 2 bits, you can write 00, 01, 10, 11, right? There's 4 numbers. But these are still just 2 bits of information, right? All I need to say to determine which one of the 4 numbers you have in your computer code is the value of the first bit and the value of the second bit. Right? Here instead, quantum mechanics allows me to make superposition of each one of these 4 states. So I can write a quantum mechanical state which is perfectly legitimate, that is some coefficient times this, plus some coefficient times that, plus some coefficient times that, plus some coefficient. So to determine the state of this 2-spin system, I need to give you 4 numbers, 4 coefficients. Whereas in the classical example of the 2 bits, I only need to give you 2 bits. So this is how you understand why 2 qubits actually contain 4 bits of information. I need to give you 4 numbers to tell you the state of this system. Whereas here I only need 2. Now if we made 3 spins, we would have 8 different states. I need to give you 8 different numbers to define the state of those 3 spins. Whereas classical is just 3 bits. If you keep going, what you'll find is that the amount of equivalent classical information contained by n qubits is 2 to the power n classical bits. And of course, the power of exponentials tells you that once you have, let's say, 300 of those qubits in what we call the fully entangled state, so you must be able to create these really crazy states where there is a superposition of all 300s being one way and another way and another way and so on, then you have like 2 to the 300 classical bits, which is as many particles as there are in the universe.
But there's a catch. Although the qubits can exist in any combination of states, when they are measured, they must fall into one of the basis states, and all the other information about the state before the measurement is lost.
So you don't want, generally, to have as the final result of your quantum computation something that is a very complicated superposition of states, because you cannot measure a superposition. You can only measure one of these basis states. Right?
Like down, down, up, up.
Yeah. So what you want is to design the logic operations that you need to get to the final computational result in such a way that the final result is something you're able to measure. It's just a unique state, essentially.
That's not trivial.
It's not trivial. And it's essentially, I'm kind of stretching things here, but I guess it's to some degree the reason why quantum computers are not a replacement for classical computers.
They're not?
No, they're not. They're not universally faster. They're only faster for special types of calculations where you can use the fact that you have all these quantum superpositions available to you at the same time to do some kind of computational parallelism. If you just want to watch a video in high definition or browse the internet or write some document in Word, they're not going to give you any particular improvement if you need to use a classical algorithm to get to the result. So you should not think of a quantum computer as something where every operation is faster. In fact, every operation is probably going to be slower than in the computer you have on the desk. But it's a computer where the number of operations required to arrive at the result is exponentially small. Okay? So the improvement is not in the speed of the individual operation, is in the total number of operations you need to arrive at the result. But that is only the case in particular types of calculations, in particular algorithms. It's not universally the case. Which is why it's not a replacement of a classical computer. Positive voltage on here. So let's say you have a battery of about, let's say, 2 volts. What this will do, you see, the